Hello, hello. Welcome, everybody. Thank you all for attending this session on multimodal vector embeddings and vector search in BigQuery. My name is Jeff, and I am a developer advocate here at Google Cloud, and I need to press the right button. I specialize in data analytics, and I spend a lot of my time working with BigQuery and its integration with our other analytic services.
Hello, I'm Marton. I'm a champion innovator and certified GDE. I work as a software engineer at a Romanian company, and I worked with BigQuery for like 10 years.
Awesome. Thanks, Martin. So today we'll begin with a brief background on vector embeddings, what they are, and then we'll move to multimodal vector embeddings. So we're moving beyond just text. Then we'll discuss vector search and discuss how to find relevant information using these embeddings in BigQuery. So this is all BigQuery, where we'll stay within that context. Then we'll shift gears a bit and talk about architectures, some common architectural patterns that we're seeing. And then we'll show two live demos, the first being an application that Martin will show about the power of multimodal search using text and images. And then in the second, I'll go into a demo of LangChain with BigQuery using retrieval augmented generation. We'll end with a slide that contains a ton of links for you, so like you can check it out, you can click on those. It's all publicly available, so check that out at the end. So we'll just begin with multimodal embeddings, what they are in general, and how they work in BigQuery. So just to set the stage and take a quick peek behind the curtain of what we use, like applications that we use every day. Chances are that many of them rely on some sort of keyword search. You input a keyword, some databases, you retrieve something from a database, and then you get some information back. And this is foundational. It works really well for a lot of applications. But when we think about the sheer volume of different types of data, and the different types of data that we're getting in now, text, images, video, audio, et cetera, these traditional databases start to find limitations. So things like nuances. How do we search when we can't just use a certain keyword, but there are synonyms? Or how do we process unstructured data like images? And this is what we'll be talking about today, how embeddings in vector search transform the way that we retrieve and interact with our information. So to understand complex data like free-form text, we need a standard way to represent it. And machine learning models can take our unstructured inputs and transform them into numerical vectors. These vector embeddings capture the underlying meaning behind your data, making it possible to compare and search based on semantic relationships, not just straight keywords. And this opens up new possibilities. Like we could find pictures using just some text, or we could find a customer support ticket that is similar to a certain, we could have an input customer support ticket and find ones that are similar, even if the verbiage differs a little bit. Now, traditionally, we think about vector embeddings on textual data. So we take text, we feed it through some sort of model, and we get an embedding out, which is just an array of numbers. This allows us to search text to text without needing exact keywords. Again, we're moving a little bit beyond keyword search, and we can search based on their meaning. So this is semantic search. Now let's take an example. Everyone, visualize in your head the word bug, B-U-G, bug up there. What does it mean? Think about it in your head. What is a bug? And now that you have a picture in your head, consider a sentence like, I found a bug in the garden today. Or here, the bug clearly refers to an insect, like a creepy crawly insect that's crawling around your garden. But what about I found a bug in my code? Or the lights up here are bugging me, or something like that. The context completely changes the meaning of the word bug. And this is what vector embeddings help with. We can turn unstructured data like text into numerical representations that machines understand, and we can capture the relationships between these words based on their context. Now, we're not just confined to text any longer, and this is what we'll be talking about today. We can generate embeddings on multimodal data. This means that text, images, audio, video, can all be represented as vector embeddings in the same semantic space with the same dimensionality, which allows us to compare all of these interchangeably for new use cases, like searching image by text, or searching videos to text, or text to image, or image to image, whatever it may be. One example might be generating product recommendations that don't just look at your purchase history, but maybe they also look at the aesthetics and styles of the images that you've been searching. So the following visualization shows, we have a graph here in 3 dimensions. And you'll see these 3 axes, living, size, and color. Now when I start to plot things on it, I have an image of a cat, and that we have a bunch of embeddings plotted on this 3-dimensional chart. We see the cat here, but then I also put some text input, a gray tabby cat laying in front of a Christmas tree. And again, we have the green dots here represent text text that has turned into multimodal embeddings. And you see that they both occupy a very similar space within this 3-dimensional domain. And this is not a coincidence, right? Powerful embedding models have learned to represent the meaning behind text, images, video, audio, and more. And because of this, we can now classify, we can search for images by text, we can search videos by text, text to image, whatever it may be, but we can classify multimedia content with impressive accuracy. So the convergence of modalities here is what's really exciting for me, and it opens up a ton of new applications for search and discovery of our data. Note that this example up here is simplified. We're only looking at 3 dimensions. In reality, our embeddings contain hundreds or thousands of dimensions that represent, or it's able to represent a lot more nuance within our data. So we're announcing this week the ability to generate these multimodal embeddings directly within BigQuery with the familiar SQL syntax that you're used to. You simply use the ml.generateEmbedding function over an object table, which points to objects in cloud storage. Again, that could be unstructured text, it could be images, audio, whatever it may be, and the embeddings are then returned directly to BigQuery. The ml.generateEmbedding function supports multiple embedding models to suit your use case. Again, we're talking about multimodal, but it also supports text embeddings as well as multilingual text embeddings. And we can just contrast this to the way that you might generate embeddings right now, which might be spinning up some Python, installing some libraries, managing your API calls and your quotas, wrangling some infrastructure to make it all happen, and then finding a suitable place to actually store that data in some sort of vector database. The point is that you can do all of this now in BigQuery with the ease of SQL that you're used to. So now that we've seen a little bit about multimodal embeddings and how they can occupy where they sit in a vector space, the question becomes, okay, given an arbitrary embedding of some sort, how do I find what's nearby? For example, we see this red dot up here, and if we give the input text phrase gray tabby cat, maybe that's the red dot on this 3-dimensional space. How do I find the closest matches to that, whether that be text, images, video, or something else? And that's where vector search comes in. So at its most basic level, vector search, the idea of vector search is to provide an input, some sort of input content, and then look through all of our catalog and find what's most, what's closest to the input. In this example we have here, we have some sort of rainbow sweater. And then we search our corpus of items. That could be your product image catalog. It might have hats, shoes, shirts, pants, whatever it may be. And then we look for the most common, or the best matches, and we rank them on the right side. This ties in very closely to our last section on embeddings, because behind the scenes, all of this runs on embeddings, right? We turn this input image into an embedding. Everything in the middle in this embedding space is embeddings too. And then we search for the closest embeddings. So there's a bit of math that goes on to find the closest embedding to our input. Then we rank the results on the right side. Thanks to embeddings, this type of search understands the meaning behind our unstructured data. Again, so this image could find maybe polo shirts that are rainbow, or I don't know, rainbow, whatever it may be that you have in your product catalog. Additionally, we don't just have to input an image. We could input a text that say, chunky rainbow sweaters, comfy, colorful, heavy, heavyweight gear for the winter, whatever it may be. The point is we can use these synonyms, and then we can get back the results that are most closest to what we're putting in. We're able to return results that are similar in nature, even if they don't share the same exact keywords, the same pixels, or the same frames within a video. So one approach to vector search, to looking through this big corpus of items, is to compare the input against every item in our catalog. This means calculating the distance between our input in every item. And that is time consuming and compute intensive. So it's probably not the best use case when we're thinking about how do we scale out to millions or billions of records. So this approach, brute force, is usually better for smaller data sets or used for benchmarking purposes. Another approach is to use approximate nearest neighbor search. In this case, embeddings in this space in the middle are classified into, I'll just call them groups. And you can see them kind of represented by these colors. So we have like orange at the bottom, pink on the left, blue at the top, whatever it may be. And the idea is that when we run a search, we only look at the group that's most like our input. So maybe that orange group down at the bottom is all sweaters or something like that. So we're only looking at a subset of our data because when we have millions or billions of embeddings to look through, it's just not efficient to look through all of them. So this approach gives significantly faster results. It's scalable to larger data sets, but it still retains impressive recall because we have this index which kind of groups things for us. Now, this week, again, we're talking about vector search right within BigQuery. This has been around for a little bit, but multimodal support within vector search for BigQuery is what we're going to be focusing on. So the idea is you could create a vector index on top of your embeddings in BigQuery. And this index is fully maintained by BigQuery. So when your underlying table mutates or changes, the index also changes automatically. It's nothing that you need to worry about. It's kind of we have BigQuery and everything is managed for you. Then you can run a vector search against this table at scale using your familiar SQL syntax. Additionally, BigQuery, again, works across modalities. So it works with multimodal embeddings. Some of the examples you may have seen in the last few weeks really focused on text. But we're expanding to other modalities as well, meaning that you can, again, unlock new use cases like searching image to text or text to image or video to text, whatever it may be. And lastly, we're also adding LangChain integration with BigQuery to allow developers to build generative AI applications with ease. So with that, I'm going to pass things over to Martin to talk a little bit about architecture and go into the first demo.
Hello, let's continue by looking at the architecture of a sample integration. So let's take step one, and let's see what is the steps that you need to do in order to start with vector search in BigQuery. First of all, input data can take multiple forms. It could be text, image, audio, video, and code itself. Step one is to encode these into vectors by using AI models called multimodal. Embedding models, so it's multimodal embedding models. These, in order to search across semantics. These embeddings are stored in BigQuery for you to use. Next, step two is to create a vector index on top of it in order to enable fast and scalable search. Step three searches the vector space based on input, which could be something similar to a text input or something similar to an image input or any modalities that you are using for the model itself. This step involves writing the select statement. For text input modalities, we can use parameterized queries and a special function built on top of the SQL in order to transform into embeddings, calling the remote AI model out of the box for you in the background. Let's go next. SQL itself isn't designed for image inputs. In the case of image inputs modality, the client application needs to fetch first the embeddings using any AI model on the market. Then this array of information can be inlined for the query itself. Finally, let's talk a bit about the output itself. In essence, step T leverages the power of vector space to return information that can vary and can be any of the modalities. Can be used interchangeably to use cases like searching image by text or searching even video by text and any combination of these modalities. Let's switch to the demo and see how BigQuery embedding generation works. And we will demo semantic search, and we created an application in order to show you the multimodal lookup tool. We have here the BigQuery UI Studio. The first step to get started is to find a data set of images in order to use for. That data is on cloud storage, and we are able to find an object table. We are able to create an object table on top of these objects in BigQuery. Once the table is created, we can check, for example, the elements. For those that are new to this functionality, we are able to get a table of paths, sizes, and different type of content type information. We need to create a remote model in order to work with fetching the embeddings. By using a remote connection, we are addressing a multimodal embedding model which is on Vertex AI. This is familiar SQL syntax for you and enables you to have a model that you can interact with later. Once this model is created, we are able to fetch the embeddings and to store in BigQuery. Here we have the new generate embedding multimodal function, which takes two inputs, the model itself, which we defined in the previous step, and an object table in this situation. This in the background lookups all the objects, could be any type of file, and it stores the embeddings for you. Next, if we look up, for example, the dimensions of this table in order to understand the context, for our demo purposes, there are 20 items, and the length of the embedding is the 1400 that we are used to nowadays. If we are looking up how this table added additional elements next to the object table details, we will find generate embedding columns with the result, the status. It could be erroring out in case of permission issues, for example, that you need to care of. Now, we have embedding stored in BigQuery. The next step is to enable vector search in order to implement the use case. In order to speed things up, we can create a vector index. What is a vector index? Vector index enables you to create like a fast way to store the distance types and cosines for your metrics. In our demo, we have few rows. And in this situation, even the model itself tells you that you need to have at least 5,000 elements in order to create an vector index. In this situation, it uses the brute force method for search. Essentially, on a business use case, you will have a lot more data in order to use for this example. And finally, step 3 is the query that we are going to run for the search itself. When I run this query, in the background, it happens 2 steps. One is we are generating an embedding for the input itself. The input right now is dinosaur. And this is a text input. And we are using the same generate embedding function as previously. And we are using the new vector search function, which takes 3 elements or 3 fields. The table where we store the embeddings, the column information where the embeddings are stored in that table, and the third one, which sources the embedding input of the query or what we ask for. We have here results that are similar to our input, and we have even instances that we can use to order by the results or set a threshold on top of it. Let's go to a demo application we have developed to understand visually better the concept. We have chosen Google Landmass dataset. We have uploaded 100,000 images in BigQuery object table on Google Cloud Storage. We created embeddings on top of it. To store the embeddings is 1 GB, and we have similar images as you see here depicted. This step of the demo uses semantic search with text input using BigQuery vector search. We can have here simple prompts like, show me a picture of a cat. In the background, we have the same two functionality that I shown on the sample itself. First of all, the input text is being transformed into an embedding, and then the search is being executed from that common table expression, how I set up this separately in our demo itself. What we see is similar images to our input. Show me a picture of a cat. As the data, it has different nuances, we can try a demo like find images with two identical objects on it. I find this very interesting because so far the technology wasn't able to establish quite nice this system. If I run this demo, we can imagine what two identical objects mean. And it will return us different kind of pictures where we see duplicates or similar identical objects on the image itself. Let's move next. And this step of the demo will use an image as an input, and we want to look out for similar images. I will use Castelul Bran from Romania, which is often linked to Dracula in a way. Let's see if it finds similar images that depict this kind of input image. Here we have two steps. First, we are fetching embeddings using any AI model available on the market, and we are getting back similar images to this query input itself. So in this demo, you have seen that generating embedding in BigQuery is a familiar SQL syntax, and you can run on top of your existing data, on top of your existing object tables, and you are able to see how vector search combines in a text and image input modality, but this can be added also for audio, video, and even code itself for it. Let's welcome back Jeff in order to show us other modalities and how to use in business use case.
Good job. Awesome. Thank you, Martin. So moving past moving past this awesome demo, I just want to show a couple of architectures that we're seeing right now with BigQuery practitioners. The first is, well, we've already gone through the first three steps, right? We have some raw data. It could be in different types of modalities. We generate embeddings on them. They could be in, you could use BigQuery as we're showing today. We could use Vertex AI. We could use other systems. The point is we're generating embeddings, and then we store them, and we're storing them in BigQuery today. The above example in blue is what we're showing, what Martin just showed and what we'll show today. It's creating a vector index in BigQuery, and then it's serving those predictions from BigQuery as well. The trade-off, there's a little bit of trade-off between the blue and the green, and that's what I want to get into. The approach up top in blue is a little bit more batch-oriented. It can take a ton of data, and it can run these searches across, at BigQuery scale, right? You don't need to manage your indexes. You don't need to manage any infrastructure. It's using BigQuery behind the scenes. However, your results might come back in a couple of seconds. Another approach down below is to use Vertex AI Feature Store. And in this case, what happens is your embeddings that are stored in BigQuery are synced automatically over to Feature Store, after which we can run online predictions. And this is going to give you results back in milliseconds, which is great for real-time, like really real-time use cases. However, the downside is that you need to manage a little bit of more infrastructure, and it's a little costlier. So these are kind of the two ways that we're seeing people start to store and serve embeddings using BigQuery right now. Now, changing the topic a little bit, LangChain has quickly become one of the most popular open source orchestration frameworks for working with large language models and to provide BigQuery users with tools to quickly build generative AI applications. We're announcing LangChain integration with BigQuery. And this will help you simplify your code, right? You don't need to you can focus on the logic of your application rather than the low-level implementation of certain details. This also enables you to get started quickly using retrieval augmented generation frameworks on top of your BigQuery data, which is what we'll show in the next demo. So in this demo, we're going to talk a little bit about large language models versus retrieval augmented generation. Just show a quick example, like why would we use RAG in the first place? And then we're going to configure and use our new LangChain BigQuery component using the BigQuery vector store. And lastly, we'll talk a little bit about we'll show how to extend these applications to powerful question and answer chains. So let's jump over to the demo and get started. All right, so just to set the stage here, in this demo, I'm going to be using we're going to be thinking about cars or automotive manuals today. And I want to ask questions about my car. So here is the Symbol Starlight 2024 Owner's Manual. Now, the Symbol Starlight 2024 is not an actual car. It is a Google made-up car that we'll be using just for today's example. But it is an owner's manual, and it does contain a lot of information that you might see in other automobile owner's manuals. So going back over to BigQuery, we will start in a BigQuery notebook. I've already run some setup, like I connected to a runtime, I imported a bunch of libraries, so we don't have to go through any of that, like not very exciting stuff. We can skip right to the fun things. Now, most people here have probably had some experience with large language models. I think we've all used them for some use case, whether that be to debug your code or ask your boss how to say something differently, whatever it may be. Many of us have experience with large language models. But you might find that LLMs don't always have the exact answer that you're looking for. They might give you something that's general. They might hallucinate. They might just say, I don't know, et cetera. So I'll be using the new, as we just announced yesterday, I think, Gemini 1.5 Pro model. I'll import that. And then I'm going to ask a question. How many miles can I drive in the 2024 Google Starlight before I have to change my oil? And when I run that on Gemini 1.5 Pro 1.5, I'm going to get some information that's like, hey, I don't have access to this. I don't know what the 2024 Google Starlight is. However, here's some additional tips that you might want to consider. Contact Google support, look at their website. We don't have this car, so it doesn't actually exist. So this is not what we're looking for, right? If we just asked a straight large language model for something like this, it's not going to give us an example. And this is because the large language model was not trained on this data because it's not public data. Well, it is public now, but it wasn't public until a couple of days ago, this owner's manual. So the idea here is we're going to move over to retrieval augmented generation. And in doing so, we'll begin with an ingestion pipeline. An ingestion pipeline, I like to think of it as we have some input. In this case, we have a PDF. We're going to ingest this document, and we're going to split it into chunks. These chunks are going to help us with better recall and generate better results in the end. So we take this big document, maybe it's like 30 pages, I don't know, and we turn it into chunks. We turn those chunks into embeddings, and then we store them in a vector database. In this case, it's going to be BigQuery. So we'll talk about the ingestion part first. Now, in order to, again, create these embeddings, we need an embedding model. And we'll use a text embedding model here from Vertex AI, the text embedding Gecko. So we'll just say that. And then we're going to ingest the PDF. So I'll be using LangChain's Google Cloud Storage file loader. I'm going to just sync this PDF over to my cloud storage bucket, and then I'll bring it into memory so that we can start using it. Now, once that's finished, we can verify that we did indeed, I mean, it says here we did load one document before we've chunked it, but I can also just verify that I do have one document name and it exists in my cloud storage bucket. So if I went over to cloud storage, we could check that out, and it is there. Next, we need to split the data, right? We need to split this into chunks, and we'll use LangChain to do that too. We'll use LangChain's recursive character text splitter to do that, and it should just take a second to do. It takes less than a second to run on this document. And we've turned this document now into 51 chunks. Now we need to turn those chunks into embeddings and get them over into BigQuery. So before we do that, I'm going to first define a data set and a table in BigQuery where those chunks and their embeddings and any other metadata is going to be stored. So I'll run that. And then I'll define our LangChain vector store, which takes inputs like the project ID, dataset, table region, et cetera. Now, I think this is kind of where some of the magic happens in this add documents against our doc splits. And what's happening here is we're calling upon our big BQ vector cars manual or vector store that we just defined a second ago. And it's taking all of those 51 chunks, and it's now turning them into embeddings and then writing them directly to BigQuery. So what was the table name? Starlight, dataset auto manual, table Starlight. So if I look in here and I refresh this, we should now have a table called Starlight. And the details, right, I just created it, or I just updated it. And if we look at a preview of the data, we can now see some information on it. We see the chunks themselves, we see the text embeddings, and we see some metadata around each of those chunks. So let's move back to our notebook. And I'll just begin by running a quick similarity search. So this is just saying, like, what are the documents that are closest to this query? Again, how many miles? Same question that we asked of the large language model. How many miles can I drive in the Google Starlight until I need an oil change? And the results are kind of ugly, right? They're just pulling straight document chunks as well as the metadata. That's probably like the top 5 here. And this is like, we could probably parse something out of this, like, I don't know. But it's a little bit complicated to actually look through. So in the next part of this demo, we'll talk about, like, this is the retrieval. Now we're going to talk about augmentation and generation. So how does that actually work? Well, I'd like to talk about the Q&A pipeline. Again, we did the ingestion part of this. We took this and we put it all in our vector database. We took a PDF, we turned it into embeddings, put it in a vector database. Now the Q&A pipeline, I like to think of it as I ask a question. The question is turned into an embedding. We run a vector search with that embedding against our database, which is BigQuery, and we retrieve the top results. Those are the document chunks. They could be images, they could be other things as well. Then those are sent to the large language model as input to augment the large language model, and then we generate an answer using those chunks. And then we return that to the smiling person here. So let's just give that a shot. What I'm going to do is define Gemini Pro as my large language model that does the summarization. And we'll use just a really basic retrieval QA chain. When I ask it, again, the same question, how many miles can I drive in this car until I need an oil change, we should get something back. And we do. So we see the query and we see the result. We see 5,000 miles until I need to change my oil. So this is great. This is something that we didn't get when we asked the large language model just a minute ago, because now we're looking at the source documents. Now, I can also go a little bit deeper and talk about conversational retrieval chains. So the idea here is that we persist the answers in memory, and then we can start to ask further questions, so follow-up questions. So here, I'm going to ask a little bit of a different question. Does my symbol Starlight have roadside assistance? The answer will be, the answer of this will be kept in memory, and we can also access, again, our chunks. So then I can ask, what number do I call for assistance? So we know that we're talking about the symbol Starlight. What number do I call for that roadside assistance? It says, I don't know. So that's not the result we're looking for. So we'll try it again. OK, there we go, 1-800-555-1212. So that is what we're looking for, and that is in the document itself. So these systems are not perfect yet, but they are getting better every day. We could then ask another question, follow up, like, what if I need assistance in a remote area? We'll see if it gives us a result here. I don't know the answer. As we run this a few times, we may get answers, we may get different answers. It's usually pretty consistent, but I guess for the live demo, it's giving us a little bit of different results. So that's where we are today on this. So the idea, though, is that we can have conversations with this. As we input more chunks and more documents, these conversational retrieval chains get better and better. So if we have one example here with, I don't know, it's maybe 20 pages of text or so. If we are able to put in more and more, we're probably going to get better search results as well. Now, there's a lot more we could do in LangChain, but I just wanted to show you kind of an overview of what we're able to do right now with BigQuery's integration with LangChain. The ability to get set up quickly, build basic retrieval augmented generation applications on top of your data in BigQuery. And just to go back, recall that just a second ago when we used the large language model, it just said, I have no idea about this car because it doesn't exist. It wasn't trained on that. But as we give it some more information and we augment it, all of a sudden we're able to get some better answers. So with that, I'll move back to the presentation. And all right. So just talking about, I just want to go over a couple quick use cases about what else we can do that's not just search. We could, embeddings in vector search allow a lot of different use cases. Like we could do some recommendations, classification based on some sort of similarity. You could even use embeddings for something like your website's clickstream data, right? You know what a path a user takes throughout their website. Well, maybe now I want to identify historical patterns or users who kind of take the same path through the website. The key point is that embeddings in vector search are flexible tools, and they work with multimodal data, so you can provide solutions in a lot of different areas. And the best part is that you can do this all within BigQuery without having to go find other tools in order to do this. So just some takeaways for this talk. The new ML.generate embedding function allows you to create multimodal vector embeddings right within BigQuery. It works with unstructured text, images, and video is coming very soon. Second, vector indexes allow you to create an index over your data for better search or for faster search and retrieval. And vector search function allows you to, it is great for analytical use cases that effectively process vector search across a huge amount of data. You can start quickly, right? You can always continue to use the BigQuery functionality that you're used to, that you've come to expect, like governance, fine-grained access control, serverless, the ability to scale up and scale down, right? You don't need to have a vector store or vector database that's persistent, that you have to worry about managing, that you have to think about the infrastructure and all of that. It's all managed for you in BigQuery. And lastly, the new LangChain implementation simplifies the process for Python integrations with open source and other third-party frameworks, allowing you to get started quickly building Gen AI applications on top of your data in BigQuery. Oh, shoot. With that, this is a page that I've put together that just has a lot of resources. You can either scan the QR code or go to the link down here at the bottom. This has documentation, blogs, videos, and notebooks that you can check out. Like, check it all out. You can click on any of these links. This is a public slide that you can use. Yeah, check that out and let me know if you have any questions afterward on all of this. So thank you all for attending. I think we have a little bit of time for Q&A, so we'll take those, and anything else we can answer outside afterward.